Hello and welcome friends. In this new video we discuss about the symbol which we are using for the differential coefficient dy by dx. Using this, we know that differential equations consist of two parts, complementary function and particular integral. So in order to find a particular integral of the differential equation, the symbol for the differential coefficient d by dx is d, which is a very convenient to use. That the nth order differential equation with constant coefficient is like this. If we write the differential equation, d n y by dx raised to n plus p1 dn minus 1y by dx raised to n minus 1 plus pny equal to x. And if m1 m2 mn, these are the roots of the auxiliary equation, then using these roots we write this above equations. Remember, we are using the symbol capital D for d by. The above equation we can write it as d minus m1 into d minus m2 dash 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 d minus mn y equal to x. Here this is same as dy by dx minus m1 dy by dx minus m2 dash dash dy by dx minus mn equal to x. This is like this. So here this term d minus m1 into d minus m2 dash dash d minus mny equal to x. So this symbol, if we consider an differential equation, second order differential equation, suppose my equation is d2 by dx square minus alpha plus beta into dy by dx plus alpha into beta y equal to 0. Then the same equation for using the symbol can be written as d square minus alpha plus beta into d plus alpha beta, it is operating on y equal to 0. And we write in terms of factor it as d minus alpha into d minus beta y equal to 0. So here you can see that if we replace for this d by dy by dx, we write it as d by dx minus alpha into d by dx minus beta operating on y equal to 0. You can see that this is a d by dx minus alpha into dy by dx minus beta y equal to 0. Now let us operate this term by term. D by dx operating on dy by dx. So we get a second order derivative d2y by dx square minus beta into, let us operate this d by dx on beta y. So beta into dy by dx minus alpha into dy by dx plus alpha into beta into alpha into beta into y equal to 0. So from these two we can take dy by dx common, and we get d2y by dx square minus alpha plus beta into dy by dx plus alpha plus beta y equal to 0. So you can see that here it is very convenient to use the symbol d for the operator d for the differential coefficient d by dx. Now whenever we have a product function, suppose that we have another type of equation like this d minus, when the roots are repeated, then we can easily see that if d minus m1 whole square y equal to 0, this is a case of a repeated root, then we can write it as 2 times d minus m1 into d minus m1 into y equal to 0. Now friend, for this d minus m1 into y, we put here it as a v, so that this equation becomes d minus m1 into v equal to 0, or this is dv by dx minus m1 into v equal to 0. So this is the first order differential equation, and its solution is, we know that its solution is v equal to c into e raised to m1 x. This is the solution of this equation. You can compare, or you can see the video on dy by dx plus py equal to 0, how to find the solution of this equation. Or let me solve this so that you will get the idea of how we have obtained the solution of this equation. Here, what is the equation? dv by dx minus m1 into v. What is its solution? Its solution is this, v into c into e raised to m1x. Okay, so we write it as dv divided by v equal to m1 into dx. Okay, so log of v minus, integrating this, on integrating this equation, log of v minus c equal to m1 into x. This is log of v divided by c, m1 into x. Taking exponential, we get v by c equal to e raised to m1x, or v equal to c into e raised to m1x, where we have separated the variables. Now this is the solution of this differential equation. Then you can see that the v equal to c, replacing, let us replace here, what is a v? V is this value, so let us replace here in this equation, which we have substituted d minus m1 into y equal to v. Then we have d minus m1 into y equal to c into e raised to m1x. This is linear equation, dy by dx plus py equal to q. And here, what is a d? D is a like this. This is like this, dy by dx minus m1y equal to c into e raised to m1x. Here, integrating factor equal to e raised to integration of minus m1 into dx equal to e raised to minus m1 into x. So solution of this equation is y into integrating factor e raised to minus m1 into x equal to integration of e raised to minus m1 into x into q. What is a q here? C into e raised to m1x into dx plus integrating constant c1. E raised to m1x, and this minus and plus, this will be 1. So here we get a solution. We get a solution here. You can see that y into e raised to minus m1x equal to c into x plus c1. Okay, now let us transfer this term to this side. So we get y equal to e raised to m1x into cx plus c1. This is the solution, and as root is repeated, we know how to find the solution of this differential equation. We have this repeated term with one term as a constant, and c into x. Okay, so using here we get the same result, just we are using the notation for the differential coefficient dy by d by dx. Now here, as you have seen, the nth order differential equation with constant coefficient is like this. just I am writing once again dny by dx raised to n plus p1 into dn minus 1y by dx raised to n minus 1 plus pny equal to x. Or in terms of operator, just we have seen that if m1 m2 mn are root, or in terms of using the as a symbol d by dx for this differential coefficient, if we use it as a d, then this whole equation we can write in short as a f of d operating on y equal to x. So whenever we write this equation in short as a general function of a d, this is my f of d operating on y equal to x. Then here the particular integral is you can see this symbol when we are using this particular integral equal to 1 divided by f of d operating on x. This is my particular integral. This solution has a two part solution of this equation. Suppose this is equation number 1, and whenever this we want to find, or we need to find the solution of this differential equation 1, then its solution contain two part. One part is a complementary function and another part is a particular integral. So complementary function is nothing but solution of this equation f of d operating on y equal to 0. When the right hand side of this equation is 0, and that solution will use us a complementary function. And to find the particular integral, we have this operator 1 divided by f of t operating on x. Now just we have seen the equation d2y by dx square minus alpha plus beta into dy by dx plus alpha beta y equal to 0. So let us consider the same equation with the right hand side x. Then in terms of the operator, we can write it as, then the particular integral of this equation is particular integral equal to 1 divided by, for this d2y by dx square we have to write d square minus alpha plus beta into d plus alpha into beta operating on x. So this is an important point to note here, that how to write the operator d. You can see that I have not written here this order equal to the indices of the operator d. Okay, so here d by dx, for this d by dx we are using d, and therefore here this is the order of the differential equation, and here I have written the same term just as a d square. Here you can see that this here is only dy by dx, so I have just write here d for this dy by dx. So you likewise I can write I have written here 1 divided by d square minus alpha plus beta into d plus alpha into beta equal to into x. Then you can see that this is 1 divided by nothing but d minus alpha into d minus beta operating on x. Okay, so whenever we operate the same operator on this, it is or whenever we operate f of d on 1 divided by f of d of x, this should be x. Okay, so you can see that whenever we operate it as a d minus alpha into d minus beta on the operator 1 divided by d minus alpha into d minus beta on x, here just interchange this factor. We can write d minus beta into d minus alpha into 1 divided by d minus alpha into d minus beta. Then alpha get cancel, d minus alpha get cancel, and we remain with d minus beta into 1 divided by d minus beta into x, again here d minus beta get cancel and we get x. So that here you can see that this 1 divided by f of d is a uh, the integrating factor, and how to find the particular integral of differential equation. So this is, so friend, this is about the theoretical part of the operator d. This operator is a very useful for finding the particular integral. So remember this these things, how to write the powers of the d, whatever may be the degree of this. The same equation here, d raised to n by dx raised to n, for this we write it as a d1 plus p1 into d raised to n minus 1 plus pn, and all these are operating on y. So this is equal to x. This is my equation in terms of d, and for this same I have written here short form as a f of d operating f of d operating on y equal to x. Okay, so friend, I hope you have get the idea of how to find the operate equation in terms of d operator d. Thank you for watching the video.